Hi, everyone. I'm Leticia. It's a pleasure to meet many of you for the first time today. Today, I'm coming from Boston, where I work with Justin Solomon at MIT. I'm a soon-to-be fifth-year student, and I'm very excited to be here at SGP because it's my first SGP in person and also my first time in Spain. And also because today I have the pleasure to talk to you about convex relaxation strategies, which is sort of a technique that has appeared in most of my work during grad school. And I hope to convert some of you to convex relaxation users today. And the goal of today's course is to introduce you to some of the important techniques and hopefully inspire you to also try to use convex relaxation strategies in your research. So here's our plan for today. And because this is quite a long talk, I thought it would be good to always keep a roadmap next to us. And we'll see this little roadmap over and over again during the talks to make sure we know where we're headed and what we have covered so far. And essentially, the talk will be divided into two parts, and hopefully we'll have time for a short 5-minute break, just so nobody falls asleep halfway through. It's near lunchtime now. But the first half will basically consist of going over some basic vocabulary, some historical motivation, and some formalities around general optimization. And next, we'll talk about what is this special property called convexity that some optimization problems have. And then we'll try to understand why do we care about convexity. And then go over some standard forms for convex optimization problems, for which I have drawn on the left this simplified taxonomy. And we'll go over each of the items on this taxonomy, and I'll give you a brief example. But probably most of the focus on convex relaxation will be on the second half of the talk, which is essentially example-based. So for different important strategies, I'll bring some graphics or geometry processing paper, and we'll see how convex relaxation is actually done in practice. So the end goal for us is to have a high-level understanding of why we would use convex relaxation, what can be done with it, and how it's actually done. So here I thought it was interesting to bring up these question words that usually you see when you're learning English for the first time. So if this is your first time learning about convexity, hopefully we'll be able to understand the why, the what, and the how. And just a brief disclaimer, what this course is not about. Because of the limited time, we of course won't cover as much as a convex optimization course would during an entire semester. But hopefully I'll do such a great job of introducing you to convexity and convex relaxation that you right away sign up for a convex optimization class in the fall. And I also don't claim that the examples that I'll present in the talk are an exhaustive list of all the work that has leveraged convex relaxation in the literature. So just keep that in mind. And once the slides are available, there will also be an accompanying list at the end of supplemental reading. If you're interested, you can pick it up. And we'll also, even for the examples that I'll bring during the talk, I won't dive into all the technical aspects because I really want us to focus on the convex relaxation aspect and to understand that we're only trying to gather the big ideas of these works. So let's get started with some fundamentals. The first thing we need to understand is why we care about convex optimization in general in this area of research. And it's actually quite a simple story. In geometry processing and computer graphics, we deal with many difficult math problems. Here, as I've just listed just a couple of them, these include solving for optimal transport problems, or finding shape correspondences, or computing geodesic distances on triangle meshes. All of these are, in some sense, difficult math problems. But the key idea in geometry processing and graphics is that many of these difficult math problems can be reformulated or rewritten as the solution to an optimization problem. So let's formalize what an optimization problem actually is, just to make sure we're all on the same page. An optimization problem, which looks like the form on the right, essentially tells you to find this unknown variable x, and the first line of the problem, which I have highlighted there, it's called the objective. And that objective has a function that tells you that function should be minimized or maximized for the x that you find. So the goal is to find this x that makes this function as big as possible or as small as possible. And optimization problems can also have objectives that are subject to constraints. And these constraints define which x's are you allowed to consider when maximizing or minimizing this objective function. And the set of all possible x's that you can consider in the constraint set is called feasible. And even though this formality, depending on which stage of your career you are, might not have come up, this should be a familiar notion from calculus, and where we learn how to optimize for multivariable functions. And the key idea there is that typically when you have some function, you can take its gradient, and to identify the critical points, so the inflection points, the maxima and the minima, you take its gradient and you set it to 0. And that gives you the critical points, and then usually what you do when you know what the function looks like is that you plug these values, these critical points, back into the function f, and then you manually classify, oh, this is a maximum or this is a minima. And if f is not a known, it doesn't have a known form, then typically we learn this notion of gradient descent, which is you pick a point to start at, and you look at the gradient of the function, and you take discrete steps along the direction of steepest ascent or descent, depending on whether you're maximizing or minimizing the problem. In this case, we're maximizing, so this will look something like this. Now, probably one of the earliest and probably the most canonical example of posing a graphics adjacent problem as an optimization problem are the so-called snake models or active contour models. And these snake models are essentially just energy minimizing splines. So if you're not familiar with it, a spline is just a parametric curve, like the one I have on the middle box there. And in this problem, we try to minimize some energy. It's called the snake model energy. And this energy encodes forces, one force to enforce or to requires smoothness of the spline to make sure the spline remains smooth during the optimization. And the other source of energy for the snake model is typically some external force that attracts the spline towards some salient feature in the image. So here I want to show you this example. Oops, sorry. So here what happens is that a user defines some initial condition for the spline. And once it defines these points, it can also define external forces that will drive the spline according to the minimization of this energy that encodes these external forces and encodes smoothness. It will drive the spline to take a certain shape or form. And the most typical application of this is to identify salient features in other geometry. So in the next example, in a bit. So in this example, what happens is that you have an image and you want to identify certain curves that are darker. What you can do is you can draw the spline next to it, And the energy that encodes this smoothness and encodes these external forces that attract the spline to the darker regions will drive the spline to sort of lock in into these dark features. And there's a lot of variations of applications of this type of model. You can detect edges, curved edges in images, but essentially the same idea and spirit that you're trying to capture these salient features that are encoded in this energy. And the typical way to solve for this energy minimization problem, so the problem of minimizing the snake energy, is gradient descent. So the same technique that you might be familiar from calculus is also used here. And even though this does a great job at all the examples that we did, it does have a common pitfall, a pitfall that is common to a lot of gradient descent optimization problems, which is the one of being sensitive to the initialization. So you might have noticed that in the examples in the video, the user drew the spline pretty close to where the salient feature was. And this is because where you draw the spline really matters. If you draw the spline too far away, it might fail to converge to the salient feature that you want. And then this is really coming from the fact that even though this is an optimization problem, it's a non-convex optimization problem. But I haven't told you what non-convex optimization problems are and what convex optimization problems are. So this is exactly what we will do next. And just to take a quick check, do we have any questions? Please feel free to interrupt me during the talk. Okay, cool. So the idea of, so optimization problems can be classified as either convex or non-convex, depending on certain characteristics. But each of these types of problems have their own unique trade-offs. So convexity has this really nice feature that if you know your optimization problem is convex, you know there is a guarantee of global optima, meaning that if you have a minima, it is going to be the global minima, or if you have a maxima, it is going to be not only the local maxima, but the global maxima. So it gives you a certificate of global optimality. Now, if you're solving a non-convex problem, that non-convex problem can have multiple local optima, and that's essentially what's going on with the snake model. If you draw the spline too far away from the salient feature you want to lock in, the spline might get stuck in local optima. So to define a convex optimization problem, there's two things that the optimization problem needs to satisfy. One is that the objective, which we just talked about, needs to be convex, and the set of constraints also needs to be convex. And if your objective and all of your constraints are convex, then your optimization problem is convex. And I know we haven't defined what a convex function or a convex set is, but we'll do that in just a second. And just for now, I want to look again at the non-convex problem. So if your problem is not convex, it's just going to be non-convex. So we sort of define non-convexity as whatever is not convex. And here I illustrated this issue of getting stuck in local minima, and why where you start your algorithm, typically gradient descent, really matters. So in this example, I have this shape that is meant to represent an energy landscape. So we'll be doing gradient descent on this shape along the surface. And what happens here is that depending on where I start, I could start on the right red dot. And if I take the direction of steepest descent, so say I'm doing a minimization problem in this energy landscape, I might get trapped at that minima. But if you observe the image of the surface carefully, you notice that the foremost white dot, so the one at the bottom of the surface, is actually the global minima, and not the one that we got stuck at. And you can start at various points, but then you might reach the global optima, or you might get stuck at one of the local optima. And so this is where this issue of where you start your algorithm really matters comes from. So if you have a non-convex problem, typically you can really guarantee that you recover the global optima by following something like gradient descent. So where we start really matters. Now, we should probably define what are convex functions and convex sets so that we understand what these so-called convex problems look like and how to identify them. So let's start with convex functions. So convex functions, you can test a function to see if it's convex by using this mathematical definition, this inequality. Or if you have a simple example, like a 1D curve, you can try to picture it. So I want us to try to focus on this big idea of this intuition. And of course, if you're familiar with this inequality, this is sort of silly to do, but if maybe this is the first time you've seen this condition for convexity, we can think about a 1D example. And the intuition behind this 1D example is that you can check for convexity of 1D functions by connecting a bowstring to any 2 points on this curve, like I have on the left, and also like I have on the right. And if I connect any 2 points on this 1D function, the function will be convex if the entire function lies below the bowstring. So in the right, you can see I have an example where I can find 2 points on the curve that once connected by this bowstring, part of the function lies above it. So the example on the right is not convex, and the example on the left is convex. But it's important to always remember that these 2 points could really be any 2 points. So to find an example to find non-convexity, you just have to pick one. But to check for convexity, you have to think about any 2 points that you can combine and connect to check for this condition. And there are certain functions that are known to be convex. And, you might be familiar with some of these, but, oftentimes when we are identifying convex optimization problems and trying to identify, is my objective convex? Are my constraints convex? We won't really, dive into a proof of convexity of a known convex function, right? You will sort of have these in your toolkit, and you're going to spot them, linear functions, and you're going to know they're convex immediately. So it's good to be familiar with certain functions that are known to be convex so that once you see an optimization problem whose objective is one of these, you don't have to think twice about it. You already know it. Now, there's also the notion of convex sets, which has to be checked for the constraints of the optimization problem. And again, we have some mathematical definition of what a convex set is. But if maybe this is your first time trying to come into terms with this mathematical definition, one simple way to understand the intuition behind convex sets is to think about these examples of sets on the plane. So these 2D examples with the triangle and the star shape. And think about what happens when you take a rubber band, you stretch around the shape and you let it go, and you let it hug the shape. To identify the non-convex shapes, you have to ask yourself, when I see this rubber band hugging the shape around it, is there any area that is not filled by the shape in between the shape and the rubber band? So in the case of the triangle, the boundary of the set coincides exactly with the shape of the rubber band. And that's what we would be looking at for convexity in sets. In the case of the star, you have these areas that are not filled by the shape, but are lie below the rubber band. And just like with convex functions, we also have sets that are known to be convex. And especially for constraints, because optimization problems oftentimes can have a lot of constraints, it's important to sort of know that these sets are just convex, by common knowledge. And another very important feature to keep in mind is that certain operations with convex sets and convex functions preserve convexity. So probably the most important one is intersection. So you might look at a constraint, and that constraint might not look like one of these sets here. So the constraint set might not immediately look like one of these here, but maybe it is the result of intersecting sets that are known to be convex. And because intersection preserves convexity, you know that you have encountered a convex constraint. So these are just some things to keep in mind when identifying convex problems. Say you're solving some problem in your research and you manage to write it down as an optimization problem. Probably one of the first things you want to do is try to determine whether this is a non-convex or convex problem because that gives you a different set of tools to solve the problem numerically with, right? And in particular, I'm going to claim in this talk that there's a number of reasons why we would like to favor convex problems or try to transform problems into convex problems. So as part of this claim, we'll go over a few reasons of why we like convexity or why we claim to like convexity. So the first reason we have already encountered when defining convexity and is the simple fact that convexity gives you a certificate for global optimality. So there are theoretical guarantees that if you find a minima or a maxima of a convex function, you know that that is the global optima. Now, another nice feature of convex optimization problems is that there are so many custom algorithms designed specifically for convex optimization problems. And these algorithms, I've described them as self-sufficient here. And I'm not sure if this is the best term, but I can explain what I mean. What I mean by self-sufficient is that you don't have to spend an inordinate amount of time tuning, for example, for initialization. So this key idea that where your star really matters for non-convex problems is not so much of an issue here. Even though each algorithm might have certain parameters, you're not really sensitive to the initialization or prone to failure in the same way that solving non-convex problems with typical approaches is. And the other reason why I would advocate for trying to find convexity in optimization problems that you might find in your research is because there are so many modern convex optimization software tools out there. And what this means is that once you write down an optimization problem, a convex optimization problem for your research, you can immediately use some off-the-shelf solution. So the prototyping becomes much quicker. And it sort of helps you to get from idea to testing much quicker than if you had a more complicated or non-convex optimization problem and you had to design a custom solution. Then you had to derive some sort of custom algorithm for it. And of course, convex optimization, custom convex optimization algorithms also exist, but this off-the-shelf software also gives you a way to double-check your work. So once you build your fancy heavyweight solver, even for a convex optimization problem, you can just try one of these off-the-shelf solutions and test your algorithm against it. And if you find bugs or if you're having difficulty debugging your code, this off-the-shelf software also allows you to go through your code and identify mistakes or to identify bottlenecks. So it's just a really nice tool. And here's just to give us some idea of how simple these are. I just illustrated here an example with a quadratic problem with one constraint, and there's literally a function in this software known as CVX. that is called quad form, and you just call that to solve quadratic forms. And you add the constraints in a quite literal way. You just write the inequalities there, and it understands, and under the hood, it will just deploy some convex optimization algorithm for you. But you don't have to worry about deriving the algorithm or putting in certain forms and all that jazz. So far, I've made a number of claims about why we like convex optimization, but I think it's important to talk about why you might not want convexity. Not necessarily because if you encounter a convex problem, you try to avoid it, but sometimes the problem that you encounter at first is just simply non-convex. And convex relaxation is all about this art of taking a non-convex problem and rewriting it in some equivalent, as an equivalent problem, hopefully, that is convex. Or at least another problem that maybe is not equivalent, but is convex, and it gives you a good approximation or a good enough solution for the non-convex, original non-convex problem. But sometimes that's not good enough. So sometimes you do a convex relaxation. You play this trick of taking a non-convex problem and trying to rewrite as some related problem that is convex. And the convex relaxation will actually give you the solution to the original non-convex problem. But the convex relaxation might not be tractable. So this is something really important to remember. Convexity doesn't always mean easier. Convexity doesn't give you a tractable problem. It just gives you those nice guarantees that I talked about. And in other cases, you might be able to rewrite this as some other related problem that is tractable, but doesn't give you the same solution as the non-convex optimization problem. So if you really care about this idea of exact recovery, so doing the convex relaxation, but obtaining a solution for that problem that is the same solution as the original problem, this might be an issue. So there are situations where doing convex relaxation might not be a good idea. Any questions so far? Okay, cool. So now we'll go over understanding sort of this simplified taxonomy of standard convex optimization problems. And just like it was important to understand that there are certain standard convex functions and some standard convex set, understanding the standard forms of convex optimization problems will help you to look at a optimization problem you see in your own research, and maybe not immediately, but pretty quickly identify whether this is a convex optimization problem. And so far, we haven't really talked about how to do relaxation. So these problems I'm talking about, they're already convex by default. Okay, so this part of the talk is not really yet about how to change a non-convex problem into something related that is convex, but really just about what do convex problems that are already convex look like. So just to help us navigate, I'm going to keep that map there. And we'll start probably with the simplest type of convex optimization problem, which is linear programming. So as you might have guessed, or you might already probably know, linear programming consists of optimization problems that have linear objectives. And here I've written really, hopefully no one catches that, but I've written an affine objective, which means a linear function plus this constant plus g. So if I had C transpose X, that would be just linear, and then affine is this linear term plus some constant. But for the purpose of optimization, adding a constant to your objective doesn't really matter. So here I'm just going to indiscriminately use the term linear, but you might see affine. And it's also subject to linear inequality constraints. And here, one thing I wanted to note is that we saw those nice standard convex sets. And I'm not sure you remember, but one of them was a semiplane. And even though this doesn't look like a semiplane, this is the intersection of a number of semiplanes. And the intersection of a number of semiplanes forms a polytope, and that polytope is convex because the intersection of convex sets is also convex. So again, sort of returning on this idea of why it's important to get familiar with these basic forms and these fundamentals so that when you spot a problem, you can understand what is the objective about, what are the constraints about, So here's one brief example of a linear programming problem that appears in graphics. And this problem has to do with the optimal transport problem. So if you're not familiar with optimal transport, and we'll sort of revisit this idea later on in the talk, but just for the purposes of this example, optimal transport essentially tells you how to move mass from one source distribution to a target. So I live in Boston, and an example that is used quite often there when talking about convex optimization is this idea of shoveling snow in your backyard. So say you have a huge pile of snow accumulating one side of the yard. Optimal transport is the world's most complicated way to transport that snow from one pile to another. And this problem here has a linear cost objective. So the cost is given by the function d. And it's linear because you don't have d squared, you just have d, first order term. And the idea here is that this problem tells you that there is a cost to transport mass from x to y, and the optimal transport problem tells you that you should transport it in a way that minimizes the cost while also transporting all the mass from the source to the target. So when you're shoveling snow, you're going to find the way of shoveling that minimizes the cost, so minimizes the effort. And you're going to make sure that everything in one pile gets moved to the other pile. So this optimization problem that I have there, Earth mover's distance, encodes this idea of transporting mass with linear cost. And this is a convex linear program. Again, sort of cementing this idea that convexity is not the solution to all of our problems, this is a convex linear program, but it has the issue that because we have the cost function computing pairwise distances between point x and y for every point in your distribution, this problem scales quadratically with the number of variables because of these pairwise distances that need to be computed. So it is a convex problem, but doesn't scale well. And there has been some work in graphics that has rewritten this as another formulation that no longer needs these pairwise distances and scales linearly with the number of variables. You can even notice that this function that is now being optimized j only depends in x, so you don't need to compute pairwise distances. And this is just an example. We're skipping a lot of technicalities of this work, of course, but I want us to really understand the big idea here that linear programs are very common. Convex linear programs are very common, but they do not always give you some problem that is easy to solve, that is tractable, that is scalable. So sometimes just having the first formulation, even if it's a simple formulation like a linear programming, doesn't help you in solving the problem. So the next standard form that we have, it's quadratic programming. And quadratic programming, it's essentially the same as a linear program, but the objective is now a quadratic. Now, you might have noticed that the square with the quadratic programming kind of goes outside constrained and unconstrained, and that's because some quadratic problems are non-convex, so they're not in this sort of convex taxonomy. To include this area outside is to include the non-convex quadratic programs. To make sure that your quadratic program is convex, you need to check that the matrix in the quadratic term, it's a positive semi-definite matrix, okay? And the intuition behind this positive semi-definite is to sort of like think about this as forming a 3D bow that is always curving up. So there's no negative curvature directions, and this sort of indicates convexity. But in practice, you just need to check, is the matrix in my quadratic objective positive semi-definite? And then the constraints are linear inequality constraints. Now, this type of quadratic problem has appeared in computer graphics. A lot of you probably, or most of you, are familiar with this very seminal work where they propose to find linear blending weights which are used for animating characters or deforming animated characters. And this problem of finding these linear blending weights in this work is proposed as a quadratic program subject to linear constraints, okay? So this is just to illustrate what these linear blending weights that come out of the optimization problem help you to do in practice. And within quadratic programming, we also have quadratically constrained quadratic programs. And these are simply optimization problems that have a quadratic objective, but their constraints are also quadratic. So they're, again, to guarantee convexity, you need to check the matrices in the quadratic terms, but now not only of the objective, but also of the constraints. So all the matrices Pi and Q need to be positive semi-definite for you to get a convex QC QP. Okay. And here, just as a fact, these are the feasible set of this problem is the intersection of ellipsoids, and that's how you can check for the convexity of the constraint, assuming that these P's are positive semi-definite, and then the intersection preserves the convexity. Okay, so quadratically constrained quadratic problems are actually something that quite often appear in a canonical application in computer graphics, which is point-to-point correspondence. So point-to-point correspondence is about matching shapes. So imagine you have a series of scans of the same person dancing, and these scans are done over time, and they capture different poses. And in these poses, you can see the different regions of the data are highlighted in certain ways, but they form a certain correspondence, right? Like the left hand is always colored green, the right hand is always colored yellow. So the point-to-point correspondence is the problem that seeks to rotate and also rigidly transform one of these poses into the other, so that one point in the point cloud that stores these poses maps to exactly one point in the other pose. And this can be formalized as this Procrustes matching problem, which is the optimization problem that I have written there. And you can see that the objective is quadratic and the constraints are also quadratic. But my question to you is whether this problem is convex or not. Anyone? I see a lot of nods saying no. Yes, Mark?
It's not because of the permutation constraint.
Yes. So this problem is not convex. And the reason is the permutation constraint. But also these rotation matrices are in a non-convex space. So both constraints give you the non-convexity. And this is the initial problem that you formulate, but later in the second half of the talk, we'll see how this particular problem can be in fact relaxed to a convex optimization problem. Now, another type of standard form for convex problems is known as second-order cone programming. So second-order cone programming, or SOCP, are convex problems of this form. So they have a linear objective function. They might have an equality constraint, but the essential characteristic of that differ these from linear programming is the existence of what are called cone constraints. So if you remember when we had that slide with the convex sets, one of these sets were cones. So these constraints essentially look like that. And one place where second-order cone programming has appeared in graphics is in this work, again, involving optimal transport. So as you can see, a lot of things in optimal transport can be formulated as convex optimization problems. And in this work, again, we look at the problem of moving mass from one source distribution at time 0 to a target distribution at time 1. And you might look at this problem, you might identify that the objective is linear, but you might be a little bit confused because we have a quadratic in the constraints, and I just said that we needed cones for this form. But this comes from an identity that is valid for any of these quadratic inequality constraints. They're algebraically equivalent to cone constraints. So you can easily transform this quadratic inequality that we have on the constraint into a cone constraint to identify this as a second-order cone program. And we'll briefly see this work again because one of the convex relaxation topics that we'll cover are convex relaxations that appear in optimal transport. So the last standard convex problem is semi-definite programming. And semi-definite programming has a linear objective function and is subject to this special type of constraint and also PSD constraints, so positive semi-definite constraints. So the variable that you're optimizing X, this matrix X, is positive semi-definite, and that is enforced in the last constraint. So here's one place where positive semi-definite problems appear in graphics. It was actually quite difficult to find a formulation of the PSD problem in papers, not because they're not that common, but because they typically show up as the result of a relaxation rather than a problem that is originally PSD. And a lot of times people won't really solve the PSD form, even though the problem is equivalent to a PSD problem. But here's just to illustrate. This is an optimization problem that shows up in volume deformation, where you sort of want to fit this deformation matrix A that encodes singular values of this deformation to another target B. And these constraints are written in this form, which is a bit complicated, but this is equivalent to a positive semi-definite problem. It just might take a little bit of care to identify it. So you see how these formulations sort of like gradually became more complicated from linear programming all the way here. But they all share the property of convexity. The only group that might not always be convex is the quadratic programming. And this takes us halfway through, and we can take a short break and then come back in 5 minutes to talk about convex relaxation strategies. Hi, everyone. Welcome back. Well, in the second half of the talk, we'll be seeing how convex relaxation has helped to solve a number of problems in computer graphics and geometry processing. And with that goal in mind, we'll go over a number of examples, which I have broadly grouped by application, but sometimes by technique, whatever felt right. But hopefully it won't be too confusing. And again, the disclaimer that I don't claim that this is an exhaustive list of all the work out there that leverages convex relaxation, but my goal is just to get you inspired and excited about these strategies and get you started on knowing some of the important ones so that hopefully you can bring that to your own research. And we will start seeing convex relaxation strategies that are used to obtain solutions to partial differential equation problems on discrete surfaces, so PDE for short. And remember that for convex relaxation, in contrast to just talking about convex optimization problems, what we're really trying to do is to somehow recast or rewrite or closely relate the known convex problem with a convex formulation. So our starting point to understand how to leverage convex optimization to obtain solutions of PDEs is a very canonical problem in computer graphics and geometry processing, which is the problem of computing geodesic distances. And of course, this is a topic that goes back so far and is so extensively studied that you could fill textbooks with it. And that's not what we're here to do today. So I really want us to focus on how this subject intersects with convex relaxation. So there will be a lot of works that we won't go over, but we will include it in some suggestions for supplemental reading. And I really want us to focus on the big idea of understanding how to leverage convex relaxation. So when I say computing geodesic distances, probably what comes to your mind is this idea of a geodesic path. Meaning if you have a surface and you have 2 points x and y, the geodesic path gives you the path that takes the shortest to go from x to y along the surface. But for the purpose of this talk, I want to focus on a slightly different problem, which is known as the one source to all problems. So in this problem, instead of computing this path, what you really want to do is compute the distance from a source point to every single other point on the surface. That's why it's a from one source to all targets problem. So one typical way to recover the solution to this one source to all target problems is to solve a partial differential equation known as the Iacono equation. So the Iacono equation is there, and typical approaches, they will solve the Iacono equation with a boundary condition. And the issue with trying to solve this equation is that this PDE is nonlinear. And in addition to that, it also can exhibit behavior with discontinuities or shocks that form as you solve this equation. So there are the issue of non-smoothness of these solutions. And still there are methods that will compute approximations of the exact solution using the solution of the Iacono equation, even on triangle meshes. But these methods tend to be very complex and also computationally expensive. So they require a lot of bookkeeping and they also require a lot of memory and a lot of computational resources to solve this. And there's a completely different approach is to recover the solution to this problem, now looking at the Iacono equation, but looking at some other formulation that allows you to approximate this. For example, the illustration that is here comes from this very seminal work, the heat method, that takes a different approach rather than solving for solutions of the Iacono equation directly. But here we're focusing on trying to solve for PDE solutions, so we'll be focusing on this problem through the lens of obtaining solutions of the Iacono equation directly, okay? And if the goal is to solve for solutions of the diagonal directly, a strategy that has been developed in recent years consists of leveraging convex relaxation. So this is the motivation behind this paper, where they propose a convex optimization method to approximate the solutions to the diagonal equation on discrete meshes. And the key insight is that we can look at this optimization problem that I've written there. And what is this? Well, it's the maximization of this function phi, and we have a linear objective, and it's subject to this inequality constraint. And in the paper, they write these bars that look like absolute values, but these are really L2 norms. So just be careful with that. And it's subject to some boundary condition. Now, the first constraint might look very familiar. It looks very similar to the equation we just saw, the diagonal equation, right? But the difference here between this constraint and the diagonal equation is this inequality rather than an equality. And the key insight of this paper is that to realize that once you relax this equality to an inequality, you no longer have a single function that satisfies the PDE with the equality, but rather an entire space of functions that satisfy the inequality, right? And functions that live in this space that satisfy the inequality are called subsolutions, okay? And these subsolutions are just functions that satisfy the inequality. And there are some results that they draw from the theory of viscosity solutions and PD analysis, which are areas of pure mathematics, that guarantee that the solution to the diagonal equation is in fact the maximal of these subsolutions. So now you can set up, leveraging this result and this observation, you can instead of looking for solutions directly of the equality, you can maximize over the set of such subsolutions, right? So now you're going to do an optimization problem over the functions that satisfy the inequality. And this optimization problem happens to be convex. It's a linear function subject to a convex linear a convex but nonlinear inequality. And now we can leverage convex optimization to solve this instead of dealing with the difficult PD with the equality. Now, another question that is adjacent to computing geodesic distances that also appears in graphics is the question of finding distances that are regularized in some sense. So what do I mean by regularized distances? So if you think about a function that is as close as possible as the geodesic distance function, but also satisfies some other set of user-defined constraints. So in this case, we are looking at two examples of functions that are as geodesic as possible, but also satisfy a Dirichlet condition, which means you regularize for some smoothness, which is a user-defined constraint. And on the left two examples, we have a localized vector field on the arms of the bear. You define some vector field there, non-zero vector field there, and you try to find the function that is as geodesic as possible, but in those parts where the vector field is non-zero, you want the function to align with the vector field. So again, vector field aligned is a user-defined constraint. And there's a lot of other regularizers that might enforce this other different user-defined constraints, but the idea of regularized geodesics is to obtain a function that is not exactly the geodesic distance function, but a function that is as close as possible to it, but also satisfying these other constraints, the regularization. Now, the key insight in this work, in this paper, is to realize that a similar technique to the relaxation leveraging subsolutions to the Iacono equation can be also exploited when you have this regularization term. And the relaxation strategy is essentially the same. You have a distance function, so you notice maybe that the optimization changed from from maximization to minimization, but it's because the integral of u has a negative sign. So when you're maximizing something, you can minimize the negative. And the constraints are the exact same. So the portion with the integral and the constraints are sort of the same thing we saw with the previous work that only dealt with geodesic distances, but not regularization. And this energy that appears before the integral is the regularization term. So their key insight is that there's theory in this area of PDE analysis, the theory of viscosity solutions, that was applied for the other problem that you can apply in a very similar way, essentially the same way to this now regularized problem. And there's even more we can do with this idea of relaxing problems using sub-solutions, or sometimes, as we've seen this work, super solutions. We can solve actually more general PDEs than the Iacono equation. We can solve second-order parabolic PDE. And these parabolic PDEs have some key distinctions from the Iacono equation. The first one is that the Iacono equation is static. So the solution of the Iacono equation doesn't evolve over time. So u in the right-hand side in the Iacono equation doesn't depend on t, but for second-order parabolic PDE, the function u depends on t, right? And the other difference is that the Iacono equation is a first-order PDE, but the second-order parabolic PDEs have a second-order term on the right-hand side. So that Laplacian term is sort of spiritually a second derivative term, right? So this is a second order. But the key insight that we had in this work was to realize that even though you have these added layers to a problem, you can break down the problem in such a way that you can still leverage similar theory to the other works. So you can apply a splitting technique. So a splitting technique essentially allows you to solve for a more complex equation by following a sequence of steps. And for each of these sub-steps, you solve a simpler equation. So it allows you to sort of break this problem of solving the second-order PDE as the problem of solving a linear but second order, and then a nonlinear but first-order PDE. So the recipe that the splitting techniques gives you is the one on the right. And the part that we leverage the convex relaxation is the equation in the middle. And the technique that we leverage is adjacent theory to the one that was leveraged with the subsolutions for the Iacono equation. But now we look at, instead of maximizing over subsolutions, we look at minimizing over the set of super solutions. But all these techniques sort of are borrowed from the same broad area of mathematics. And they all consist of sort of relaxing an equality, like the one you see at the PDE on the right, to an inequality, like the one you see on the constraint of the left-hand side problem. So if we take 1 second to look at this, the PDE on the right is actually precisely what is discretized in the constraint on the left. But again, we relax the equality with an inequality. And adjacent results to what was used for the static first order case can be used for the time evolving second order case, thanks to the splitting and some other results. But this is sort of the broad idea. I know we skipped a lot of technical problems, but hopefully you got excited about these works and you follow up with additional reading afterwards. But it's sort of this idea of solving these PDE solutions using a convex relaxation strategy. In this case, these sub-solutions and super solutions, and coming from this theory of viscosity solutions. Now, another broad application set, or a set of problems that convex relaxation strategies appear in, is our mapping problems. So we already sort of touched upon one of these problems, the point-to-point correspondences. And in that case, we saw that was initially posed as a known convex problem, right? So just as a recap, we saw in the first half of the talk, the Procrustes-Matchy problem, which is the way you would naively pose this problem of rigid transformations and rotations that match one pose to another. And, I asked the questions, is the convex? Mark said, no, I agree. And I promised that there would be a convex relaxation for this problem. So here we are now. So the Procrustes matching problem is a non-convex, quadratically constrained quadratic program. And this is a form of non-convex problem that typically can be relaxed to a semi-definite program. So the key insight in this paper is that this particular non-convex QCQP can be relaxed to an SDP, but at the cost of exactness. So this is one of those convex relaxation cases where you can write a convex relaxation, but the solution to your convex relaxation is not the same solution as the solution of the original problem. So again, convexity for the win, but sort of depends, right? If you really care about exactness, this relaxation will be of no use. But what they sort of uncover in this work is that the solutions that you get from the convex relaxation are good enough for this application, in which case we're perfectly happy with a non-exact solution that comes from a convex optimization problem. And there's a lot of steps in the relaxation of a QCQP to SDP, and I thought there would be more interesting things to cover. But I want us to sort of stick to the big idea here. And what they do on the paper to go from this non-convex constrained quadratic program to a convex SDP is that they introduce this new variable. And this new variable is secretly a function of the rotations and the permutations. But once you rewrite the problem in terms of these new variables, the constraints in the original problem that were quadratic become linear in the new variable. But this comes at the cost of two additional constraints imposed in this new variable. One is that this new variable needs to be positive semi-definite, and the second one is this needs to be rank 1. And the rank 1 constraint is a non-convex constraint. And we're happy with the PSD constraint. So what they do is just drop the constraint. And this is precisely why the solution to the relaxed problem is not the solution to the original problem. You can magically drop a constraint and hope for the best. But in this case, even though it's not an exact recovery, it's good enough for the application. And I would encourage you to maybe take a deeper dive into this process of going from the non-convex QCQP to the SDP, because it's actually a type of relaxation that appears quite often in graphics research. Now, this is not a proper relaxation technique, but it's something that will help you to obtain a convex problem, which is, with the Procrustes matching problem, what we did is, relax the original problem formulation, drop a constraint, obtain a convex problem. But another strategy that helps you obtain convexity is to, instead of relaxing the original formulation, is to rethink the problem statement. So this point-to-point correspondence, it sort of requires an all-to-nothing map, meaning each point maps to a point or it doesn't, right? And what they do in this work is to replace this all or nothing mapping requirement, right, this bijection requirement, with linear probabilistic maps. So now each point is allowed to map to different points with certain probability distributions, right? And by looking at this relaxed problem, so allowing this notion of a probabilistic lens of this, instead of this point-to-point correspondence, for the same type of matching problem or shape correspondence problem, allows you to pose this as a convex optimization problem. So it's not a proper convex relaxation, but it's oftentimes something worth considering. If you have a non-convex problem, can I relax my problem statement rather than relaxing my non-convex optimization formulation? As promised, we'll go over convex relaxation techniques for optimal transport, where actually a lot of the formulations are convex or can be relaxed to convex problems. So we briefly mentioned how the optimal transport problem is sort of this canonical problem of moving mass from one distribution to another at minimal cost, right? But this problem was initially posed as this formulation here. This is known as the Monge's original formulation, and it basically tells you to find a deterministic map that tells you for each point in one distribution where to send it to another. And this map is deterministic and is sort of analog to this notion of all or nothing, right? So one point will be assigned in one distribution will be assigned to a single other point in the other distribution. And this original formulation is not convex. And the non-convexity comes from this constraint. And if you're interested, you can think about this set of all such deterministic maps, and you can determine this set, this constraint is not convex, by thinking about linear combinations of these functions, of these deterministic maps. These linear combinations will not necessarily map the source to the target, so they'll violate the constraint. Now, something that happened, which typically happens when you encounter a non-convex problem, is that people have thought about ways to relax this problem. In particular, we have this famous Kantorovich relaxation, which was proposed by Kantorovich, and does something sort of spiritually similar to the idea of relaxing a point-to-point correspondence to something you allow mass splitting. So now, instead of looking at these deterministic assignment maps, you allow each point in the source distribution to map to points, plural, in the target distribution with certain probability weights. So some of the mass coming from one point will map to another point and maybe to some other points as well. So this idea of allowing mass splitting and relaxing the actual problem statement rather than the optimization formulation. And this Kantorovich relaxation is a convex problem. So the objective is linear or quadratic, depending on your cost function, typically. So for the work on above, which we briefly saw earlier in the talk, the cost to bijective is linear, so you end up with a linear constraint. And the second one, there's a quadratic term for the cost function. And these constraints are basically telling you that all the mass has to be moved from the initial distribution to the target, and these are simply linear constraints. So this is a convex problem. Now, there's another version of the same story in which instead of looking at these as simply this assignment problem, you look at the optimal transport problem as a dynamical problem, meaning that you think about mass flowing rather than just being simply, assigned somewhere else from the source distribution to the target. So there's the idea of a time variable in which you can see intermediate distributions that interpolate between the source and the target. And the original formulation for this dynamical version of the optimal transport problem is known as Benamou and Brenier. And this formulation is not convex. But a simple change of variables allows you to rewrite this as a problem that is jointly convex in its variables. So now it will be jointly convex in this new variable m, which is momentum, and the density mu. And in the original problem, the problem was not convex in terms of the density mu and the velocity v because of the coupling of these two variables in the first constraint. You have this mu multiplying by v. That coupling caused the non-convexity. And in general, this trick of doing a change of variables when you have coupled variables is something good to keep in your toolkit because oftentimes changes of variables that are analog to this will allow you to decouple these variables in a way that gets rid of the non-convexity. And then this work, it's essentially discretizing this version of the problem, the one on the left-hand side, and also another version of the same story that we saw earlier in the talk. So optimal transport is like this area full of problems that can be massaged into convex problems or are already just convex already. So I would really encourage you, if you're interested in this, to take a look at these references and other additional reading. And the next type of relaxation that shows up in graphics, and this gets a little bit more abstract maybe than these problems that we can picture, but hopefully I'll do an okay job in getting you to understand and be inspired by this type of relaxation. And this type of relaxation is the sum of squares relaxation, or SOS for short. And the starting point to understand this relaxation is to look at this setup that I have here, where you have, on the left-hand side, you have a domain, D, and this domain, we'll define it as being compact. And the boundaries of this domain are the intersection of polynomials, okay? And then you have some function, x, that maps points in this domain to this patch that you see. So you can think of this patch as some sort of height field that sits on top of the domain D, okay? So these points P1 through P6, they actually, on the xy plane, they sit on top of the original red points on the domain D. So in a sense, there is a function, like a height function, that tells you how high to go, but the x and y coordinates are sort of fixed by the domain. And this mapping from the domain to R3 gives you that patch. And here's where things get a bit more abstract, but let's focus on the big ideas. There is this thing called the Putner's positivity theorem. And Putner's positivity theorem allows you to say that if this function, this height function that we have defined that tells you what is the height of these points on the patch, if that function is polynomial, then the checking for non-negativity on this domain can be done by just checking if you can express this function as a sum of squares of polynomials. So this might seem a bit complicated, but the big idea here is that this theorem gives you a certificate for non-negativity. So checking for non-negativity can actually be surprisingly difficult, and this theorem allows you to not have to check for it directly, but as long as you satisfy certain conditions, you can instead check if this function satisfies being a sum of square polynomials, okay? And checking for SOS condition, it's easier than checking for non-negativity directly. So it's sort of a certificate. You can check for this other thing, and then you know that this function is non-negative. And you might be asking, why would I care about this non-negativity business? Well, it turns out that we oftentimes have optimization problems that simply look like minimizing some function f. But this function f might be a super non-convex, complicated polynomial. Okay? There are actual applications where this happens. How would you even check that this super complicated non-convex function satisfies non-negativity, right? So there's a way to equivalently write this optimization problem on the left as a problem with linear objective. And by introducing this constant sigma, and then introducing the constraint that f is greater or equal to sigma, okay? Now, instead of checking, this is again something where you have to check positivity for the constraint. Instead of checking for that, you know you can check for the SOS condition, okay? So I know that some details might have been missed, but the big idea here is there's a lot of problems where your objective is very complicated and you need to check for positivity. You can rewrite this as another problem that has a linear objective, so no longer non-convex, but the constraint requires you to again check for non-positivity. And instead of doing that, you leverage this theorem as a certificate for non-negativity. So you can check whether f minus lambda is a sum of square of polynomials rather than checking that that quantity is actually non-negative. And this actually has practical applications. So in hex meshing, you can formalize the notion of quality of a hex mesh using these non-negativity conditions. So for example, in hex meshing, there's a lot of problems involving the quality of the mesh where you might have tangle elements or inverted elements. You can pose conditions on the quality of the mesh that can be written as a non-negativity constraint. And then for those problems, you can check for the SOS condition instead of directly checking for that, for the non-negativity constraint. So just to wrap things up, hopefully we won't be more than a couple of minutes over. The last type of relaxation that I thought it would be interesting to cover, and again, this is a no-exhaustive list, but I tried to be a little bit diverse on different ways to think about convex relaxation a little bit beyond your proper relaxation strategy. And so I thought as a last topic, we would talk about something slightly different than going from a non-convex problem to some related formulation that is fully convex. So there are some problems that you might encounter in your research. A lot of them exist involving elasticity and dynamics or parametrization, where unfortunately there's no way to get rid of the convexity in all the variables of the problem. And some problems just have that nature. And in this case, it's still worth for checking for a type of convexity, so not full convexity, but what is called is a hidden convexity. So a hidden convexity is essentially a convex substructure for a problem where you might be able to isolate the non-convexity into maybe one of its variables instead of all of its variables. So now you can leverage some of the benefits of convex optimization because you have some variables for which the problem is convex, but you still have a non-convex part that you sort of have to deal with. But sometimes things work out. And these are the examples that I brought of such cases. They all deal with this idea of distortion energies. And distortion energies essentially tell you that to form an object with minimal distortion, you have to minimize energies that look like a function of the deformation gradient. So the deformation gradient is this sort of mapping that takes you from this rest pose to a deformed pose. So imagine you have a mesh, it's at an initial pose, it tells you how do you deform it to get to a deformed state rather than the rest state. And many of these energies, these distortion energies, are actually nonlinear elasticity models. So they're not convex in the deformation gradient. And if you minimize this quantity and your optimization variable is simply the deformation gradient, you're sort of stuck with this fully non-convex problem. But one thing we can do is to apply a polar decomposition of the Jacobian and rewrite this problem as, instead of an unconstrained minimization problem, as a constrained minimization problem where the objective is simply the distortion energy, but now only as a function of the stretch component, and the constraint enforces the polar decomposition into rotation U and stretch component P. And then for some energies, the function that was originally a function of the deformation gradient will be only a function of the stretch component. Not all energies, some of the energies you get stuck with the U and the P, as F will be a function of U times P, but some other energies, you can express them as simply a function of the stretch component. So now your known convexity, it's isolated in the rotation component in the constraint, and your objective is convex in the variable P. And some of the energies where you can apply this decomposition, apply this polar decomposition and then obtain the known convexity isolated in the rotation include as rigid as possible, so ARAP energy, symmetric gradient, and also symmetric Dirichlet energy. So this unlocks being able to leverage some of the benefits of convex optimization for some tests like parametrization, static deformation, volume correspondence. And in this work that I had on the other page, they show that a modification of a standard convex algorithm works with some of the same guarantees for this not fully convex, but this problem that has the hidden convexity. So you still have some nice theoretical guarantees that are proved in this work. And you follow a very similar procedure to a standard convex optimization algorithm with a simple modification. Now, this is just a brief preview of something else that you can do, also leveraging this hidden convexity, which is, this minimizing anelastic energy typically gives you a solution to a static problem, meaning, you fix some of the control points on the octopus mesh. You might, pin some of its arms, and then you minimize the energy to figure out what the rest of the octopus looks like, right? So these are known as static deformations because the octopus will deform from the rest state to some final state, but they're not dynamical. You're not seeing the octopus deforming over time, right? There's just no kinetic energy. There's only elastic potential being minimized. So from physics, we know that if you add dynamics, you can write this quantity known as the Lagrangian, and it's essentially a kinetic energy minus an elastic potential, right? And to figure out the equations of motion, you minimize the Lagrangian. So you gotta minimize something that looks like kinetic minus elastic. And even if you apply the hidden convexity to the elastic, right, you have that negative sign there, right? So you have a convex function, kinetic energy is a quadratic term, so it's convex, minus the elastic potential that you might have applied the hidden convexity, just like in the previous work, but that minus sign sort of messes things up because then you have convex plus concave. So it's not really obvious at first, but what we did in this recent work is that we massaged or basically we cooked up another problem, and this problem has a convex terms plus another term with the heat and convexity and no minus sign. And we show that the first order optimality conditions, so the critical points of the new problem, coincide with the critical points of the first problem. And then with this, we can leverage the same sort of modified convex optimization algorithm for like dynamical problems with this heat and convexity. And well, with that, we sort of cover some fundamentals of general optimization. In the first part, we talked about why we care about convexity, how to identify convex problems. And in the second half of the talk, we went over many examples roughly grouped by application or sometimes technique, where we saw some important strategies to go from non-convex problem to a convex formulation. And this week, my challenge to you, at SGP, we'll see many works where you see some application, geometry processing, or graphics being framed as an optimization problem. Can you identify some convex relaxation strategy for these problems? Especially if the paper mentions that they get stuck at local minima or they have a non-convex formulation, can you think about leveraging a similar strategy to some of the ones we covered today, or a different one that you might find out with some supplemental reading? Can you figure out a convex relaxation strategy for the optimization problems you see this week? Yeah, that's it. Thank you.